known globally. But for those of you who are not familiar with Geoff, he is our Chief Advisor for Hydrogeology for Piteau Associates globally. He's got 41 years of experience in surface and groundwater control across the mining industry and has worked in over 60 countries worldwide in every major industrial commodity and in all climatic zones. He is very well known, especially in the open pit dewatering sphere, but has extensive underground mine dewatering experience as well, and has worked on pretty much all of the world's largest mining operations and has had significant involvement with the Large Open Pit Group. Geoff has also co-edited, along with John Reed, the recently published CSIRO Guidelines for Evaluating Water and Pit Slope Stability, and has contributed chapters to the Guidelines for Open Pit Slope Design, the Guidelines for Open Pit Slope Design in weak rocks, and the Guidelines for Mine Waste Dump and Stockpile Design, coincidentally co-edited by our CEO, MarkHawley. I think that about sums Geoff up. So Geoff, if you'd like to share your presentation and take it away.
You need, yeah, the host has muted me, hang on.
We can hear you, that's good.
Can you hear me? Can you see me?
Can't see your screen yet.
I think you need, can you see that?
It's starting now.
Yeah, we can see it.
Can you see the laser pointer?
Yep.
Yeah, all good.
Yep.
Okay, so welcome everybody. Good morning, good afternoon, good evening, wherever you are. This is called Introduction to Open Pit Mine Dewatering. There's a lot of material in here, so I'm just going to have to ask you to strap yourselves in, and we'll deal with questions at the end. So I'm going to cover topics rapidly: how water affects mining, principles of mine water control, dewatering methods, passive water control, the difference between dewatering and slope depressurization, some slides on surface water, prediction of dewatering rate, numerical models, and monitoring. So we'll start off with how water affects mining. This is an old slide I've used for many years. Essentially, there's two considerations. One is operational. If you go and get the water out, you don't mind. But there's a host of ancillary cost considerations that go with that. The second is slope stability, and water pressure is always detrimental to pit slopes. And if you can remove the water, you can usually steepen or optimize the slope, and potentially on a large pit, we look at about $500 million per degree of slope angle for one of the larger operations. So just some examples of costs: safety, drilling, sampling, ore control, blasting, loading, haulage, processing, mineability, all affected by water. So just some example costs. There's been a couple of recent studies done, one in Chile on this. Blasting, if wet, can cost incrementally between 100 and 300 bucks per hole. Haulage can give you 2 to 3% more weight in the truck, more if you're mining soft materials. Can take 4 to 5% off your tire life, give you up to 5%, 3-5% maintenance, and increase your loading costs by somewhere around 5, 6, 7%. So there's a couple of studies. So all those cost considerations are affected by water. We deal a lot with operations who physically can't do sinking cuts because they can't load blast holes because of water pressure. When you do that, it's best to do an investigation, because a lot of the times the water moves down the slope from above and just moves across the floor in the subdrill. So it's best to kind of think about why the water's there. So this is a project we did at a mine in Chile, where we drilled some holes. They couldn't load the holes, they couldn't make the cut. So we drilled some holes, we looked at the structure so we could see where the water was. And we put in 3 temporary dewatering holes, cut the water table down, and give them the opportunity to mine deeper. And at the same time, we looked at it from a bigger picture to achieve some overall dewatering. So water always has a detrimental effect on pit slopes, and there's a whole host of discussion and reasons for this, but essentially water changes the resistive forces in the slope and creates driving forces. There's other reasons, it mostly pertaining to soft rocks, volumetric changes, weight, chemical changes. But in hard rock mines, we think about the resistive forces and the driving forces. And the most important concept of water in slope stability is the effective stress concept. It's quite simple when it boils down to it. You have any type of surface, any type of failure plane, two forces acting on it. One is the downward pressure of the rocks, which is trying to hold the structures, hold the materials together. The other is the upward weight of the water, which is trying to push the materials apart. And this can be fractured rock, it can be a fault, it can be porous medium. So the effective stress is just the difference between the two. So it's the difference between the total stress of the weight bearing down and the upward force of the water. So clearly, if you can reduce the water pressure, you will increase your effective stress. You'll increase the shear resistance on this failure surface. And I always like to think of it as two planes of glass. If you put two planes of glass together without any water between them, if you try and move them, you get frictional resistance. A little bit of water between them and they'll go all over the place. And the harder you press, the more the upward force of the water, the more difficult it is to keep those panes of glass together. So it's quite a simple concept, just relationship between the downward weight of the materials and the upward force of the water. On a simple flat surface, it's probably not going to shear, not going to move. So where it comes into practical application is when you have oriented angle surfaces. And so what the water pressure does is try and lift the block and reduces the frictional resistance to sliding. So if you don't have water, you've got the full weight of the block and you've got the frictional resistance on this surface. You put water between that, it pushes that surface apart, it reduces the frictional resistance to the sliding. So it's a simple concept. This is just another diagram, put it into a slightly bigger picture on a slope. So this is prior to dewatering, prior to depressurization, this is your water surface, this is your failure plane, obviously. You reduce the water surface, you reduce the upward force of the water, and the thing you increase is the frictional resistance on that failure surface. And so in geotechnical engineering, you can't change the nature of the rock, you can't change the structure, but you can change the water pressure. So it's the only parameter in a rock slope that can be readily changed or managed. So that's resistive forces. You have to also think about driving forces. A couple of examples here where we have a structure behind a pit slope, as was the case here, structure directly behind this slope. Water pressure behind it, dewatered in front of it, driving force at the toe of that structure. This was a double stack failure, took out the ramp, mostly due to the pressure behind this behind this fault zone. Toppling is something we also have to deal with in mining a lot. So this is a typical toppling situation, in if you have a slightly in-dipping structure or joint set with water pressure behind it, you can increase the toppling potential, as happened here. So this is a saprolite actually with very strong foliation. The water got into the foliation joint sets, which have become dilated because of the slope, and created this toppling situation. The other driving force that you often see in coal or in soft rock mining is piping. This is a coal mine in South America where you can see the sand layer has been forced out, has been eroded by the water pressure in the sand. And what often happens is that sand layer erodes, undercuts the materials above, and leads to instability. So think of resistive forces, effective stress, driving forces, and those are the key factors that water plays in geotechnical engineering. So what we're trying to do with slopes is cut them as steep as possible usually, which minimizes the amount of waste material we have to strip at the top and maximizes the amount of what we get at the bottom. And won't go through this in detail, but if we have take the water out, we can look at potentially steepening or optimizing slope. And as a worldwide average, the indications are that whatever you spend in terms of dollars depressurizing the slope or dewatering the operation, you have a 5-to-1 payback in terms of improved slope performance. As geotech engineers, we always faced with the cost being on our general manager's radar screen, and we often do a poor job quantifying the payback benefits. So one of the things I like to do when I get involved in projects is make sure the operation understands the value of the money they're going to spend on water. Just an example of weak rock. This is a slide I've used for a number of years now. So it's a shale, and you can see they lost a flood protection dike, flooded the base of the pit. It was a stable slope. Water got into the shale, expanded the material, and you can see the consequences for stability. So some general principles of mine water control. I'll go through a few examples. With an open pit, we're trying to lower the water table. So we're trying to get the groundwater table, drop it below the pit floor to give us access for mining and all the inherent benefits to go with that: cost reduction, improved slopes. Underground, we're often trying to work below the water table. So we're often in harder crystalline rocks below any near surface water zone. So a fundamental decision in any underground mine is whether we encourage the water to come in. If we do that, we have to manage it. But if we do that, it reduces the rock pressures around us. Or do we exclude the flow, which means we don't have to manage it underground, but it does mean that we've got maximum rock pressures as we advance the headings. So for underground development, it's usually necessary for the early development to mine through water. Even if the mine's deep, you've got to get through the near surface zone to get there. And so that usually requires some kind of dewatering, even if the production operations don't. And I always think this is a good example of the difference between open pit and underground. So this is right now an underground mine. It's in breccious and crystalline rock. They have to deal with very, very little water underground because they're below all the near surface aquifer formations. As soon as you put an open pit through this, you've got the water in the quartzites, in the sandstones, in the upper pit walls, and you've got the stability issue in the shale units. So it turns it from a very relatively dry mining operation into one where water management becomes fairly significant. So that's a good example of the difference between open pit and underground dewatering. So just to look at the large dewatering programs, and I've listed what it may not be the top 10 exactly, but it's pretty close to being the top 10 dewatering projects. And if you look at the settings, you can basically come up with 4 settings for where the big dewatering projects are. One is Nevada, where you have very large alluvial basins, which have a huge amount of groundwater storage, and sometimes connected to carbonate rocks. In Southern Africa, we have the Copper Belt, and we have large dewatering operations in dolomites in South Africa, in Zambia, in the Congo, really related by dolomites and driven by ongoing recharge. In Europe, the large operations tend to be due to sedimentary basins, and they tend to be soft rock or coal driven. And then the new one, I guess, is the Pilbara, where we're getting a lot of the iron ore. Mines are finding connections to dolomites and other carbonates, and the amount of dewatering in the Pilbara is increasing, and the Pilbara is becoming a fairly major center for mine dewatering. So this is an example. This isn't one of the top 10, but it's a mine in Canada in limestone that produced 1,000 liters a second. It was ringed by dewatering wells, and we also put dewatering wells inside the pit. So the largest hard rock dewatering project I think there's been is Barrick Goldstrike in Nevada. It's an example. It's a very large block of interconnected carbonate rock. And this is their history. So they started dewatering in 1990 and went on till, well, it's still going on, but this graph goes to 2010. So they've created, at this point, about 1/2 kilometer of drawdown. And to do that, to remove the storage, they had to get up to about 4,300 liters per second. So you see, once they reach that steady state, the dewatering rate tails off, and their steady state pumping rate is just over 1,000 liters a second at the moment. So they've actually tagged an underground mine onto this, but the open pit has pretty much historically dewatered the underground, although going forward they need to do a little bit more dewatering. So it's a big carbonate block, strongly bounded. The exact opposite of this, in a couple hundred miles down the road, same formation, but very, very strongly bounded. Very, very strong fault boundaries. So these are similar, or same formations. This is the Ruby Hill mine in Nevada. Similar formations, very high permeability, but very strongly bounded, with the result that this particular project only makes 35 liters a second. So it's not the permeability of the rocks themselves that control the dewatering, it's the presence or absence of these structural boundaries. A couple of other examples. This is Lefakani, close to home to Lodi in Botswana. It's a good illustration of it's impossible to dewater a flat aquifer. What happens is, as you dewater it, as you lower the water table, you reduce the saturated thickness. As you reduce the saturated thickness, your well yields go down. As your well yields go down, you need more and more wells to maintain your dewatering rate. Consequently, you reach a point where it's no longer economic to put in more wells, and you have to deal with a seepage face. So this mine's always had a seepage face at the top of the sandstone, but it illustrates the impracticality of dewatering the sandstone. You could potentially do it from below easier, but most operators will do it from wells, and it's essentially not possible to dewater a flat aquifer. So many of us are used to dealing with saprolites. It's not usually possible to pump water out of saprolites or out of weather material, but it is quite often possible to put in wells underneath, and saprolite typically has good drainage characteristics. So if you reduce the waterhead or water pressure in the weathered rock underneath, you can typically underdrain a saprolite, and there's many examples of that globally, how wells have been put in underneath to pump relatively small amounts of water to underdrain the saprolite above. You do the same in weathered rock. Many weathered rocks would be similar to this, although in porphyry, in the leach cap, it's the contact between the leach rock and the primary rock underneath is quite often very tight, and so it's very difficult to fully drain the leach cap. And here's an example where you've got, even though the slope is quite well dewatered in this case, you've still got ongoing seepage from the bottom of the leach material. So I threw this one in. This is an underground, but it's a good example of how to approach dewatering. I'm putting it for some of the guys in Ireland who might be listening. This is the Lachie mine, which was mined. It finished about 4 years ago. It was an ore body at about 200 to 300 meters depth in very, very caustic cavernous limestones with the water table on the surface. So to drive a decline, the decline was laid out in tight shale rocks, So we're in the situation where we're driving the decline and we have to come out in the ore body, which is impermeable rocks, which are now under 250 meters of head. So there's a couple of ways to do this, but what they elected to do in the end was put in a surface well field. So put in wells from the surface to pump the head down a little bit, so that when they actually came out of the bottom of the decline into the ore, the head was reduced and the water was more manageable. As soon as they got underground, they were able to put in an underground drainage system and the wells became redundant. So the wells only operated for a couple of years while during development, after which the underground system took over. And this was also a large dewatering project, peaked at about 1,100 litres a second. So a good example of the situation you're faced with driving a development into a permeable aquifer. This is Grasberg, which is an interesting case. Very, very karstic, very, very permeable rocks. And they had the foresight at the start of the Grasberg pit to put in a drainage tunnel underneath. You can see it's in the bottom of the sink line, so the water naturally wants to get down into the bottom. So excellent planning from the operation initially to put a tunnel in, and that tunnel has taken care of all their dewatering requirements over the life of the pit. They've got some weak materials in the slopes which they have to deal with locally, but essentially the tunnel has served them good all the way through the project. And one interesting thing about Grasberg is it's so karstic, and the flow rate is so permeable that if you put a tracer on the surface here, it appears within the tunnel, typically within 24 hours or less. So very rapid cycling of water. Another interesting example, this was another underground mine. This one I worked on in Poland for a while, and another high pumping rate, but half of that water came from one fracture zone. This was a picture I got from KGHM where they just hit the fracture zone. This is a photograph I took. So all this water that you see here was from one fracture zone. So that tells you when you're working in carbonates and karst material that you can get some very, very high localized inflows. So as well as dewatering, you've got to think about what to do with the water, and these days the cost of managing the water can be more than the cost of getting it out of the mine in the first place. So it's something that has to come onto the radar screen, the downstream cost. So sometimes we design the dewater system to optimize the water quality and to intercept the water before it reaches the ore body. So we may end up pumping more water, but we have less treatment, less downstream costs. So that's a consideration. Another issue is the impact. So this was the hydraulic barrier at the Carboneras Cruces mine in Spain. We kind of designed this when Rio owned it about 25 years ago. Essentially, they pump from dewatering wells from the periphery, and they inject into wells about 2 to 3 kilometers out. This is the aquifer they're trying to protect, which forms part of the water supply of the city of Seville. And so we put this system in to create a hydraulic barrier and to reduce the impact. It's served its purpose. It's still operating, and the mine's still going. Somewhat easier is to put in rapid infiltration basins. Again, this is a large open pit, again in carbonates in Nevada. We pumped close to 2,000 litres a second out of this. We put in these infiltration basins here to prevent the spread of drawdown and to discharge the water. This is the hydraulic map, so you can see the kind of drawdown. And again, these rapid infiltration basins have operated well. This is a 30-year-old design which continues to operate, and so it's been a relatively low cost and efficient way of getting rid of the water. So just some methods. Active dewatering, which is what most people do. Passive dewatering, which is not something that's done in open pits, although I'll show you an example. And combination. So if we're trying to passive methods, if we're trying to grout or to try and slurry walls, they could be localized within a bigger picture dewatering system. So the methods: pumping bores, interceptor bores, peripheral in-pit, horizontal or vertical drains, drainage tunnels, passive methods, sumps, and increasingly on our radar screen is surface water. So in-pit bores, probably 50% of all mines worldwide have in-pit bores one way or the other. This is an example. We put them, you can always work with mine planning, find some real estate in the pit. Here's a good example. Here's a bore that ran in this pit for 5 or 6 years. At the intersection of a ramp and a catch bench, we widened the catch bench slightly and gave us the real estate to operate the bore. This is a sleeper mine in Nevada, which operated for 15 years in the 80s and the 90s. It's a classic dewatering system where it produced, again, about 1,000, 1,200 liters a second. 80% of the water was from this gravel aquifer. So we had 40 dewatering bores in a line on the west wall, dewatering this gravel aquifer, leaving 20% of the flow to be taken from peripheral bores on the west side mostly, which is where the water came from, and then a relatively small number of in-pit bores. So that's a typical combination that you might use for an open pit dewatering operation. This is the same thing visually. This is another mine in Nevada where we've got, in this case, about 35 bores on the outside of the pit, pumping from alluvium. We have our in-pit bores at the toe of the slope. And this particular case, we need to increase locally increase the drawdown within the alluvium close to the pit wall to increase stability. So we created a dewatering bench here, and we have a line of 25 small bores producing relatively low flow, but keeping this face underneath nice and dry. Directional drilling is becoming something on people's radar screen. As far as I'm aware, there's 3 mines that now operate directional bores. They tend to be expensive, but they enable you to get the bore outside of the pit, and therefore it doesn't get in the way with operation. The big take-home message, the thing we've had most problem with is anything else, is that you can't run full weight on bit when you're steering. And so the thing that's given us more heartburn than anything else is because you're not running full weight on bit, your penetration rate and therefore your cost has the potential to escalate. But directional drilling will become more and more in the future, no doubt. So why do we do what we do? Well, there's the hydrology, obviously, but operations, we have to tailor the flows. We may have pumps already. We try and maybe stage our costs. Environmental reasons are becoming more important, and the need to optimize cash flow, particularly early on in the operation. With dewatering wells, it's important to understand that the pumping water level in the bore bears no relation or little relation to the pumping water level in the aquifer. So there's 4 components of drawdown. There's the true drawdown in the aquifer. There's our localized drawdown as the velocities increase through localized fractures. That tends to be the biggest drawdown component. There's the flow through the well screen and the gravel pack if there is one, and there's the turbulence in the well itself. So it's important to realize that when we do a dewatering bore, we may have a pumping water level down here, but our benefit is only this. So it's important to design these things with minimal well losses. Similarly with depth of fracturing, we have 2 bores here in the same fracture zone. This one hits the fracture zone at 100 meters, this one at 200 meters. We start off up here and get good yields from both. However, we get down with 50 meters of drawdown, the yield on this one is halved because the fractures are shallow, but the yield on this one has only gone down by 25%. We come to this point, this one's now dry, this one is still serviceable. So depth of fracturing is really important when we're siting dewatering bores. And pilot holes, so that's why we tend to do pilot holes. Here's an example from a project in New Mexico that we work on. So there's a couple of pilot holes here. This one just gets a generic increase in flow due to the submergence. So we're all dubious about whether that's got sufficient flow to sustain a pumping well. Here we have low flow, but we see this big jump in flow here, which corresponds to fractured horizon. So we know that this particular pilot hole has good yield, and it has yield at a good depth. So it is a good site for a production well. So to find that out, we drill pilot holes, and most operators now optimize production well locations with pilot holes. Many operators have to blast around wells. This particular one that you're looking at is a kind of a model blast. There's $2 million worth of production well inside this blast. They've cut as much free faces as they can. They blasted from with long delays to this free face. And this particular operation, it runs big equipment. It runs 4,100 shovels, as you can see, large trucks. But they run a lot of input wells, and they're able to preserve wells through 15, 20 benches. So they have a very big experience of mining and preserving production wells during blasting. Another consideration is if you're looking at wells for slope stability, you may have to, in this particular case in Peru, we're trying to depressurize this zone to stabilize this surface. So we have no option but to drill bores through it. Yep, they shear, and yes, they get affected, and we may have to replace them, but we have no other option to depressurize this and to stabilize, as this was a pretty large tonnage failure, as you can see. We have no option but to put our bores through the failure surface. So one slide on passive water control. This is a slurry wall around a coal mine. It's done to exclude the water in alluvial material, which is actually driven by a river. The issue you get with passive water control is keying this into the rock. So it's okay in the alluvium, but you've always got a shattered or a weather zone in the rock, and it's very difficult to stop the underflow in that. And once the underflow starts, you can lead to piping, and it reduces the effectiveness of the barrier. The other thing is, if you maintain a head on the outside, you could potentially push more water through deeper system. So, question, dewatering versus depressurization. So, some examples here. So each of these diagrams, the slope on the right is well dewatered. Slope on the left requires depressurization here because of adverse structures. So we need to penetrate these structures to depressurize them. Here, because we've got clay or argillic material, which holds up the water, we may be able to dewater underneath, but the water holds up in the clay. And here, where we've got a flatline structure or lithological contact, which also requires maybe some vertical drains through it to get rid of the water pressure. So 3 examples where you need depressurization. This is a case where the mine's completely above the water table, or where you might have recharge from a river affecting the clay zone, or just general infiltration giving you perched water. So those are some examples of when you need depressurization. Most mines now, most big mines globally use horizontal drains. There's lots of types of equipment. They're ideal for penetrated these type of structures, so releasing water behind structures. Lots of different shapes and sizes. So here's an example of one wall with 2 applications. So this was a pit slope with a clay altered monzonite with a limestone behind it. It would have been impossible to depressurize the monzonite without dewatering the limestone. So we put in long drains into fractures in the limestone to dewater it, and then shorter drains into the monzonite once we've done that to get the water pressure out of the monzonite. Sequencing with mine planning is always a fight. So it's always necessary to plan this in advance and to work with mine planning. Here's an example where they're mining a bench at Trim Shot, and yet mine planning has allowed them access here to put in drains to depressurize the slope. Vertical drains, again, this is where we've got a perched water zone with the dewatered rock underneath. The purpose of the vertical drains is to convey the water down into the material that's already dewatered and into the wells, rather than having to put dedicated shallow, low yielding wells into that zone. A couple of slides on underground drainage galleries. There's probably about 7 or 8 net mines now with underground drainage galleries purely to depressurize slopes. You can see with horizontal drains, as you dewater, the less and less of the drain is in saturated material, so the drains become less and less efficient. Whereas if you drill from underground, you're always drilling under high head material. The drains are more efficient if you put them in underground because the driving heads are higher. So some operators now where they have a large pit typically and a longer term requirement will look to drainage gallery. Here's an example, and it's not the drainage gallery itself that does the depressurization. It's the holes drilled off of it. So you can see there's a ring of holes in this particular case. It's obviously not cheap to put in, but this one will serve a purpose for many years to come and give some great flexibility with mine planning. It enables them to change the design in the comfort that their slopes are well depressurized. And just some pictures of a typical underground drainage situation. So surface water is becoming really high on the radar of many geotechnical engineers. So what we're beginning to realize is that the majority of instability in slopes occurs within 50 meters of the slope. It's where the material becomes weathered. It's where it becomes dilated, deformed, where you have blast damage. And some recent research suggests that over 50% of slope movement can be correlated with either surface water or precipitation. So surface water is becoming a key role, playing a key role we begin to realize in depressurization and slope instability. And it's because where you have pressure increase shallow in the slope, if you think back to your effective stress diagram, you've got less weight on top of it, and so the influence of a small increase in pressure is greater. So this is a typical situation that we deal with. This is a mine where we've got the rock nicely dewatered, and when they actually did a numerical model to show that there was no problem with water, and yet they had a multi-bench failure. And this is very, very common where we have water in the alluvium or the weathered zone up top. That water runs down the overbreak zone. It's the most permeable and the least resistant. And the common situation is where you have a structure that's parallel to the slope. That structure dilates when you mine it. The water runs into the structure. It has nowhere to go, so you have a driving pressure, and can be a factor that contributes to instability. We start to see this situation an awful lot. So it's not the groundwater per se. It's the water from the upper zone, alluvium, the weathered material or rainfall, which runs down the surface and creates instability. So how do we deal with this? Drainage on ramps. This is the slide I use more than anything else around mines to try and get them to improve drainage on ramps, to shed the water out of the pit using the ramp. So a nice crossfall with a greater cut channel, easy to maintain, and it gets rid of the water, keeps it away from the slope, keeps it away from the operating faces. So this is a kind of using your ramps is becoming a key player. It's something that I tend to push a lot. So it's an example of these are all ramps, and they've put in a drainage system on this particular slope, and they've engineered it based on where the ramps are, and they've put in various sumps to deal with the water. So just one slide on how to predict the dewater rate. There's 3 things you can do, really. There's a water balance approach, which is probably the most pragmatic and most reliable because it doesn't rely on a knowledge of permeability per se. Analytical equations, where you simulate the mine void as a large diameter well typically, and you look at radial flow to it. You can add in various flex barriers and anisotropy on top of that, or the numerical model. So people often think the numerical model is a panacea. In fact, it's less reliable than the water balance approach, because with the water balance approach, you're taking the storage of each unit, you're taking the recharge, you can empirically derive the estimates, and it's typically the most robust approach, particularly in the early stages of a project, purely because it allows you to think about the assumptions. Whereas in a numerical model, you're relying on permeability and storage, whereas the real control on water isn't permeability, it's the ability of water to cross boundaries. Essentially, it's due to water availability, not permeability, and water availability, of course, is more better predicted with a water balance model. So anytime you do a prediction of mine water and benchmarking with other sites, typically there's somebody done it before you, there's somebody in a similar situation. So benchmarking is a key part of the process. So just a couple of things on numerical models. It's a hot topic at the moment. There is quite a bit of research being done on numerical models. A couple of guide points here. Any models, you should think about what it's trying to do. Don't just build a model. Think about what you're trying to do, the scale you need it, and the complexity of the system. And so there's no really such thing as a one model fits all approach. If you have a regional model, it's not going to be very good for slope depressurization, which is something we see time and time again. And people ask me, is it best to use mod flow, fee flow? It really doesn't matter, because the code selection is really very small consequence compared to the knowledge of the site, particularly the geological uncertainty. The biggest source of error in the model is the geological uncertainty and therefore the conceptual understanding of the site. And I think more and more people are beginning to realize that it's the bigger picture assumptions that drive the model rather than the small scale details. So an example, I think, as part of the LOP, we've pretty much established that it's fine to use equivalent porous medium models. It's fine to use our off-the-shelf models, our mod flows, fee flows, CWs, for virtually any mining modeling situation, even in fractured rock. So fractured rock fits the equivalent porous medium mode quite well. There's no need to run out and do specific fracture flow models. But we can now, particularly with the sophisticated codes, we can populate the model grid, the equivalent porous medium grid, with anisotropy, discrete features, barriers, and we can put our hydrogeological interpretation into the model. But when we look at a model, let's not just think about the model, let's think about it holistically. And this is the bit that makes or break the model, is the interrogation. Looking at the model and saying, is this real? Is it right? Does it match what we expect? So this is an important part of any modeling process, the interrogation of the results. So an example I use, this is a model. I've showed this to many people, and I say, right, what does that mean? And people look at me as if they look at it as a geotech or hydro, look at it, and very hard to understand what that's telling them. If you put a couple of virtual piezometers in, you can see what the model's predicting in terms of pressures, heads, and gradients. So you can see here the model's predicting a downward pressure towards the crest of the slope and an upward pressure on the toe. Purely just by the differences is the way you present the results, makes it easier to understand and makes it easier for people to see. So finally, a couple of slides on monitoring. Monitoring and reconciliation is any important. It should be any dewatering system should be this loop. So design, implementation, monitoring, verification feeds back into the design. Same for geotech, same for hydro. So this monitoring and verification is an essential step in any execution. And the thing that I say that's helped the mining industry, or helped the hydrogeology in the mining industry more than anything else, is the advent of the vibrating wire piezometers. Now we can put many piezometer sensors in a particular hole. We can put them in vertical holes, upward holes, angle holes, horizontal holes, and it gives us this fantastic data set, so we can see what levels are depressurizing and what levels aren't. So this is a hole where they've got 10 sensors in them. It's a slightly bigger hole, so put more sensors in, so you can see the vertical discretization and the response to drains and the response to wells. Very clear and so you develop a really robust understanding of the hydrogeology based on the piezometers. So if there's one thing that's moved mine hydrology forward in the last 10 years, it's the advent of the vibrating wire piezometer. So you can put multiple instrumentation in one hole, cement them in or grout them in very quickly and very cheaply. So let's set ourselves targets. Here's an example of the piezometer hydrographs, and we have targets. So if we're in the green, we know we're good in terms of operations and slope stability. If we're in yellow, we've got an acceptable factor of safety. If we're in red, it's somewhere we don't want to be. So we can plot our hydrographs on, forward track them, and adjust the program to make sure we stay towards the green and out of the red. So good to define targets and accountability of the program. And finally, this is the final slide. Just again, the monitoring networks we have now are very good. This is another old example I use. It's still a good example of horizontal drains. So you can see here, this particular slope was unstable. It was showing up nicely on the radar as deforming. So this is going back to 2013. So in December, we're getting significant movement on the radar. Put in 12 horizontal holes, and the radar 6 weeks later was the deformation had significantly reduced. So it's a great way of putting in the horizontal drains and knowing very quickly what those drains are buying you. So that was a really very quick trip through the procedures and some examples. So hope you enjoyed it, and probably got time for a few questions. I don't know how the questions will work, but we've got a few minutes for some questions. So thanks very much. I appreciate you all attending this. I appreciate you all taking the trouble to get online, and thanks very much. And yeah, any questions? So Gus, maybe
thanks, Geoff.
I'll stop sharing, shall I?
Yep.
Yeah, that'll be great. Thank you. So you can either put your questions into the chat or just raise your hands. And while we're waiting for your questions to Geoff, I have some questions for all of you. So if you could just tell us where you're logging in from, and then any questions for Geoff?
We've got a couple of questions on the chat already. I think the first one was from Kez Murray. He asked, are there production borehole constructions that are more resistant to shearing than others? For example, steel versus UPVC. Do you want to take that,
obviously.
Geoff?
Yeah, you still hear me?
Yep.
Yes.
Okay, so steel's obviously better, and thicker wall steel is even better still, but it obviously drives up your cost. You can also put play into the wellbore where you know where the failure surface may be. You could put in some different gravel materials to give yourself some play, and you can also drill larger diameter so it takes longer for the shearing to take effect. But I think what we found more than anything else with wells through shear zones is if you keep them operating, they reduce the effective stress locally around the bore itself. So if you keep them operating, the local effective stress around the bore gets minimized, which reduces the local shear. And that, I think, is what we found to be the most robust thing, is just to keep them operating. And there's lots of times where the wells have operated fine, they've gone offline, and as soon as they've gone offline, they've sheared because the local effective stress has increased, has increased. Hope that answers that.
Yeah, we've got another one from Edgardo Zogolig. My apologies for the pronunciation. He asks, what is the best way to fight against surface water occurring during short time duration but huge amount of precipitation? He says you've passed over ramp control relatively fast. How effective is this as a methodology?
So the ramp control is your bread and butter. Unless you do ramp control, you've got no chance of making anything else work. So you essentially create drainage on as many ramps as you can. And if you had wide catch benches, you also add the drainage to those catch benches. And so that is really the main thing you can do is just do as good as possible as your input, what I call drainage arteries. And I guess make sure they're maintained. And of course, the issue obviously in a large rainfall event is if you get local collapse of the slope or local failure of the diversion. And so it's when you're laying out these things, you've got to look at the slope above, and you may want to mesh certain parts of the slope so they don't collapse. The other thing to think about is to look at your system and think, right, what happens if this fails? And design the system with a failure point, with a weak point. So if it's going to fail, it fails in a particular location, which then allows the water to go where you want it to go, rather than an uncontrolled place where you don't want it to go. So there's a few things. So one is your input, your ramps and your catch benches are your bread and butter. Make sure you look at ways of things or reasons they might collapse during a large event. And then thirdly, design with a weak point. So if it does fail, that water goes somewhere where you want it to go rather than where it doesn't want to go.
Thanks, Geoff. Kes Murray, I see we've got a second question from you. If you don't mind, I'd like to take a question from Jose Ardito and come back to yours, Kes. Jose asks, have you got experience covering upper cracks from landslides, either using geomembranes or other materials, to avoid rainwater entering those cracks or instabilities? Have you seen that done successfully?
Yeah, good question. I mean, I'd be hesitant to do it with geomembranes, purely because you could, if you got more movement, you could pull the geomembrane apart. Normally, you would do it by either filling the cracks or by grading over them, or by doing it, doing it on the surface. I have not got any experience with geomembranes. I've never needed to use geomembranes for that. But I can see in particular applications, they may be useful, but again, it's damage to the geomembrane. I've been in lots of situations where we've got geomembrane lined channels, and we've had deformation of the channels, and the geomembrane has torn or broken or cracked. So that's the key thing, is to protect. If you're going to use it, make sure your geomembrane gets protected.
Following on from that, Geoff, Murkan Ozbakir has a question asking whether input drainage channels need to be impervious, or do you just recommend drainage on ramps without any sort of impervious lining?
So normally just drainage on ramps without any impervious lining, but it's a site-specific situation. I was looking at one recently where there was scour on the drainage channel, so it made sense to actually put in a clay-lined channel at the base of it. We've done lots and lots of concrete lined channels in pits. Again, they're harder to maintain. So really, if you can avoid lining, do so. If there's a specific need to line, you should line. Again, try and avoid geomembranes because they get damaged, they get eroded, they get weathered by the sun. The water can go underneath them. Geomembranes are quite hard to manage in a open pit drainage situation. So the answer to the question is, if you can avoid lining, do so. If there's a specific need to line, do it.
If I can add to that, Geoff, following on from something you said in answer to the previous question, was also be mindful of what the drain is running on top of. Be mindful of diverting water from strong rock onto weak rock, for example. And you may need to think about lining a portion of the channel rather than the whole channel. Jumping back quickly to Kes Murray's question, he asks, have you ever had to deal with open pit mining in an unconfined aquifer, where there's a concern that pit unloading stress on the lower confining layer leads to upwelling of groundwater and a resulting failure in the confining layer? If so, what's the process of assessing that risk?
Okay, so just read that back to me again, so make sure I get the confining and the unconfining bit straight.
He's asking about an unconfined aquifer, which has a confining aquifer underneath it that's potentially impacted by groundwater upwelling from the lower confined aquifer.
And so in terms of slope stability?
Yes, I assume so.
Okay, so any method to get the water out of the lower confined aquifer is good, because it's going to reduce the effective stress in that lower aquifer and increase the stability. How you do it is another matter, and if you're transferring water from the lower unconfined, the lower confined to the upper unconfined, you then need to think about what the consequences of that for the upper confined aquifer. But essentially, any method to get water out of the lower confined system is beneficial. So normally you wouldn't transfer water. Normally you would deal with it specifically with measures in that unconfined system. So, for instance, I've got a mine at the moment where we've got just that. We've got an unconfined sand at the top. We've got 300 meters of clays, and we've got confined fractured rock at the bottom. And the way we deal with that is two different systems. So we put in bores, wells specifically into the upper layer, into the unconfined layer, and we put dedicated pressure relief bores into the lower layer. And the idea is that we pump from the lower layer and allow the intervening clays to drain down and depressurize.
Right, we've got
thanks very much. Could we please, Frank Lloyd Mills, you've been very patient. Do you want to ask your question?
Thank you, Geoff, for the presentation. I just had a quick question. So with horizontal drains, what happens to the pressure at the end of the drain? So say you put 400 feet of drain into the wall. At the end of that drain, what happens to the pressure?
You mean that you mean 400 foot down the hole?
Yes.
Yeah. So it's exactly the same as a well, but on its side, right? So you put in a drain, and you get depressurization all the way around the drain. So going on from the end of the drain, if the drain will have an effect past the 400 feet, but that effect will get less and less with distance. So you'll get depressurization past the end of the drain for sure. Well, depends on the geology, but typically you would. Am I answering your question, Frank? Does that give you an answer?
Yeah, that gives me an answer. I just wanted just to see what don't you have the tendency of tapping into something you don't want to at the end of the drain if you don't seal it off, if possible? Absolutely,
you don't want to do that. So one of the cautions with horizontal drains is make sure you don't tap water that you don't need to. It's not a common situation, Frank, but it's just something that you always need to think about. I was just talking to one of our guys about it yesterday. In fact, are we drilling these drains too deep? Are we bringing water close to the slope that we don't need to? Particularly given the fact that we're all starting to realize now that most instability occurs at shallow levels. So, you can get into a situation, as you well know yourself, you can get into a situation where you have water comes in the end of the drain, flows out of the near part of the drain, and actually creates damage to the slope. I think you've been in that situation yourself, Frank.
Right.
So it's a good point. So most of the time it's okay, but again, you do have to think of the site specifics.
Thank you, Geoff, and thanks talking to you again.
All right. Yeah, we'll see you soon.
All right,
Yes, you're up with some more questions.
Can we carry on? There is a lot of interest, obviously. Just scrolling up a little bit, Akash Chowdhury asks, at what stage of mining is dewatering generally done?
It just depends on the operation. So you typically want to get as a purely a general rule of thumb, you want to get the water table 20 meters down below the pit floor. So it just depends on what situation you're in. If you're in a really permeable, confined and disconnected system, it can be a month. If you're in a big groundwater unit, it can be several years. So it just depends on the geology. So the example I showed you from Goldstrike, you know, they started dewatering on that, and you know, they were pumping 4,300 liters a second. That's the largest dewatering project ever. And so, you know, you can see the rate of drawdown, and they had to make sure that the rate of drawdown was greater than the rate of pit floor advance, which is why they had a very, very aggressive mine plan, and that's why they had to pump so much water, is because they had to create drawdown within a very large aquifer to keep the bottom of the pit floor dry.
Thanks, Geoff. I'm just double checking I haven't missed any specific questions there quickly. I think Ray Philippe, thanks for joining us. Ray is asking, do you consider different water qualities with respect to water dewatering projects, especially considering potential downstream water treatment cost requirements?
Well, absolutely. You have to, you know, you have to consider water quality, one, in terms of the well itself and the materials you use, and particularly so in underground. And if you know, we were just looking at a block cave situation recently where water quality at the block cave was determining what materials they use for underground support. So there's the engineering side, and yes, absolutely, for the water quality side. And if you can put your wells in some upstream locations, so you don't suck the water through the ore, and therefore improve the quality, then quite often it pays to pump more water to doing that, and avoid the treatment costs, and so you can release the water directly. So absolutely, but there's two reasons. One is materials and engineering, the other is downstream treatment and impact.
Two specific questions that have come up a couple of times. The first one, first asked by Arnaud Hamidou. He's asking if you can elaborate slightly on the re-injection, the hydraulic barrier deep aquifer injection slide in Spain.
Oh, it's a long story. You know, it was done 25 years ago. It still operates. So one of the issues, of course, in you know, that project's fairly close to the city of Seville. So one of the issues was getting locations to put the injection bores. We knew conceptually where we wanted them, but you can't just put them everywhere because somebody owns the land. So it was trying to design a system given the land constraints. Another issue has been with water quality. So it's in a dipping basin, so there is a water quality gradient across the site. So that was also an issue. So there's been some operating issues, and there was, you know, another thing that happened is that a change of European drinking water regulations between the time it was designed and the time it was operated has caused the system to require some water treatment, which wasn't in the original design, and that came about because of a change in regulations. So it's a long story. The full answer would be over a few beers, and it's still going on.
Yeah. Nolan Ondas asks, have you ever dealt with mud inrush to an underground mine, and is active dewatering an effective way to solve the potential mud rush issue?
Again, depends on the situation, as it always does. The answer to the question is yes. I'm quite sure there'll be a few guys from Grasberg on the line. But Iwan Sechuan at Grasberg has done a great job over the years putting in a peripheral dewatering system to the DOZ and latterly the DMLZ to reduce the water peripheral to the block cave and minimize the amount of water that goes through the draw points. So the short answer to the question is yes. The longer answer is, you know, some situations you can't do it, but where you can, then definitely.
And that follows on to the next question, actually, from Arthur Magondo. He's asking, how do you control water recharging from the footwall of a production in an underground tunnel, besides just directing the water to a sump?
If it's giving you issues, you should drill it and take the water out of the formation before it gets into the workings, because then you can manage it and you can keep the workings drier. So if you know where it's coming from and there's an opportunity, drill it with underground bores.
A quick one from Mantamane Sehole, which I'll answer. He asks, what laws govern how much water you can pump out during dewatering? Is it up to the mine, or are there international or national laws that restrict the amount? Quickly, that is down to local legislation, specifically where you are, but you would generally have to apply for a license based on your understanding of how much water you need to pump out in order to achieve your goals. And then it would be up to you to license that amount or get approval to pump that amount. But I'm not aware that there are any numerical restrictions on how much you can pump independent of any characterization or study.
No, there aren't. Yeah, there aren't. But for instance, that rapid reinfiltration basin that mine in Nevada, where we had those 4 rapid reinfiltration basins, in Nevada they want you to return as much water as you can to the aquifer as possible. So many of the operations in Nevada, for instance, operate rapid infiltration basins so that the water goes back into the aquifer. The thing you obviously have to be careful of is recirculation. So yeah, I don't know. I'm pretty sure there aren't any restrictions on the amount you can pump. It's more the restrictions on what you impact.
Thanks, Geoff. Motlachi Molabe has asked, do you think well-managed mine dewatering methods can reduce issues of acid mine drainage in the long run?
Yes. You know, again, you can, typically you can design your system to minimize contact with reactive rocks. So again, it's purely a matter of costs, including downstream and treatment costs and handling costs. But a lot of the times it pays to get the water slightly upstream of the operation, or certainly away from the reactive units, so that you end up with less mineral acidity being mobilized into the flow stream.
Following on from that, Liam Quinlan has asked that you've mentioned an increasing environmental focus on mining, and he noticed the case with artificial barriers. Is the dewatering framework developed with a long-term consideration for post-mining remediation on a mine site, or short-term considerations?
Yeah, always. So virtually in any jurisdiction nowadays, the initial permit and the initial license application has to have a closure plan. And one of the issues that we face in the mining industry is to get the right balance. I think it's important that we don't get too sophisticated in our closure requirements too early on. So we have to, when we're permitting, we have to demonstrate that there's a system to close the mine which minimizes impact or which creates acceptable impacts. But we don't want to put too much detail into that, because when we operate the mine, we always improve our understanding, and things that we thought might work early on may not work once we know how to operate the system. So yeah, closure has to be considered all the way through. And in fact, you mentioned the LOP books. You mentioned the LOP books earlier on, and there's been 5 books that the LOP have produced, and we're just embarking on a 6th book, which is purely focused on mine closure, open pit mine closure.
Those books actually are available on Amazon as well as from the CSIRO website directly. And they're seminal works, and certainly I've started using them as handbooks and recommend them as handbooks to everybody who's involved with mining in general and water management in particular. Hendrik Grobler has asked, he mentions that his company is evaluating long in-pit horizontal drilling with limited characterization of the groundwater system surrounding the open pit. The rock mass is high K, and he says that it seems like an understanding of the structural system that acts as a conduit for the water system would be required. Is systematic drilling good or poor practice in unknown systems? I assume he means, do you go ahead with the drilling without a full characterization first, or do you need to characterize the system properly?
So typically you would do a pilot trial. So you would set up the system. So you put in 1 or 2 multi-level piezometers. I don't know whether this is a greenfield site or whether it's an operation. So presumably it's a pushback if you got the ability to do horizontal drains. But so you would put in a couple of piezo's and you do a trial with, if it's permeable, you'd probably do 4, 5, or 6 horizontal drains. You do them at various lengths and you do them at a couple of different spacings. And you would see what it did to the piezo's, and you would design the system based on that. As a very broad guiding principle, the longer you drill, the better, because the longer you drill, the more the hydraulic contact. But you've got to make sure you tailor the specifics on top of that. And as Frank pointed out in a few questions ago, it's very important that you don't drill too deep and capture water that you don't need to. So I guess to answer the question is, yeah, you'd go forward with it, but you'd do it as a pilot trial and you'd evaluate the results of the pilot trial.
You mentioned bringing water where you don't want it. Proper reticulation of horizontal drains is very important to make sure that you don't introduce water into the overbreak zone inadvertently where there might not have been water beforehand.
Yeah,
so,
that's normally not normally good practice to reticulate drain flows.
Yeah, at least grouting it of a starter casing and potentially a PVC casing in the hole as well. Still a lot of questions coming in, Geoff. Are you still okay for time to carry on for a bit?
Yeah, I'm just gonna keep talking. I'm just gonna grab some water here, but keep talking.
If I could just suggest that we continue until 2:30, after which time you can perhaps take your questions to the guys via email. Is that okay?
So we've got another 10 minutes. Yeah, I'm certainly happy to hang around. And as Geoff said, he's available still for a while. Geoff, a question from Cardiansa. He's asked if you can provide a bit more detail about your last slide showing horizontal drains that have reduced slope movement, as shown by the radar.
Well, that was a site where at the time there were no piezometers, but we knew the geological structure quite well, and there was clearly movement on the radar. As you can see, it had been accelerating for a few months, and so the decision was made to put 12 horizontal drains in there. You know, you can see the instantaneous results on the radar. The deformation slowed down, and the slope became more stable. So that's an example I always use. But there are now, you know, most large pits have got radars in one form or another, and so there's getting to be quite a few good examples now of deceleration on radar correlating to installation of drains or installation of pumping wells. So yeah, it's an old slide. It's the slide I've used. It's actually in the Weak Rocks book, I think. But there's quite a few other examples of that these days.
All right. Sorry, just making sure I haven't missed any questions here quickly. There have been quite a lot. Sorry, last question I answered was from, Hendrik. Vadim Lochnikov asks, what would your recommendations be for drainage in the wall where the primary mode of failure is toppling? For example, shallow but frequent horizontal holes, or anything else that you'd recommend?
Yeah, so probably horizontal holes. It again depends on the situation. You know, there's a pit in Canada that it's a couple of large pits in Canada that we've worked at for many years, which are kind of the I guess the standard of toppling. All walls have major toppling, lots and lots of deformation, and the depressurization program is centered around horizontal drains. They do lots of horizontal drains. They have up to four drills going all the time. So yeah, because toppling is typically controlled by steep structures, then it's a good geometry for horizontal drains. So you're trying to get water out from behind the structures. But one of the things we have learned over the years, or one of the things we try and focus on over the years, is to actually focus the depressurization below the area where the toppling is occurring. So we try and get below the active operating bench. We try and get below the area that's toppling and depressurize that. And the goal for that is to depressurize in advance of the operation. And so to reduce the effective stress in the structures before they topple, and therefore to defer the onset of toppling for as long as possible. And if you defer the onset of toppling, typically you defer or you reduce the total amount of movement because of the toppling. So yeah, horizontal drains, and if you can, focus on the intact rock below the toppling to increase the strength of that material before it topples.
Okay, thanks, Geoff. Toppling. Omalade Ade Ajayi has asked if you have any recommended specific method for dewatering from boreholes or wells specifically. I assume he's asking if there's a recommended design for dewatering from wells.
Yeah, so the most efficient design for a well is a hole in the ground with nothing in it, because as soon as you start to put anything in it, you increase the well losses. So in fractured rock, a kind of rule of thumb is drill a hole, put in perforated casing, but try to avoid a gravel pack. And if you need a gravel pack or a formation stabilizer, keep it as coarse as possible. And the reason for that is in fractured rock, when you drill the hole, you would tend to drive cuttings into the fractures. If you have a gravel pack, then when you start the well, or when you develop the well, the cuttings will come back down the fractures and will clog up the gravel pack. So if you don't have a gravel pack, you avoid that from happening. And there's lots and lots of examples of mines which used to have gravel packs, which don't anymore, or which have coarse golf ball size gravel formation stabilizer, purely because the gravel pack gets plugged up by cuttings which come out of the fractures during development of the well.
Thanks, Geoff. Quick one from Marble8229. He says, thank you for the presentation, and also asks, how reliable would you say is pore pressure data from vibrating wire piezometers? I.e., how well does it represent what the pressures actually are at the levels they are placed? And how can you confirm that on the ground?
So these days they are highly reliable. So the source of errors are typically result from hole instability and therefore creation of pure grout seals. There are lots of mines these days who have got vibrating wire sensors side by side with standpipe piezometers and show the same responses. There are lots and lots of mines where we've got two vibrating wires, two vibrating wire piezometers close to each other, which show similar responses. So these days the instruments are very robust. The manufacturers have done a great job with them, and there are tons and tons of papers written to provide data to substantiate that question. So these days very reliable, but it's the same as anything else. You have to look at the data and you have to question it, and if you know, if the data doesn't look right, then you know, maybe there's another reason for it. The one problem with vibrating wire piezometers, if you're doing a standpipe piezometer, you're measuring from a known reference point, so you're measuring down the hole and you know where the reference point is and you know where the water table is. With a vibrating wire piezometer, you are measuring from the instrument up, so obviously you can't see the instrument once it's been in the ground, so you are relying on the driller counting the numbers of pipes, the driller or the technician making sure that the instrument goes in at the right level, so that you know if the instrument's reading a given pressure, you can translate that into a total head because you know precisely where the instrument is. So one of the things that's important when you put these in is to constrain the installation techniques, to have good QA procedures, and to make sure that the sensor is where you think it is. And you know, just the tons and tons, hundreds and hundreds of vibrating wire data points every week, and the vast majority of them are very good. So very reliable is the answer to the question.
Yeah, and the critical point as well is knowing what unit you're measuring. So you need to know where your sensor is, but also what the rock is around it. Is it on a joint, on a fault, on a particular lithological unit?
Yeah.
So you need to know what you're measuring. Yeah. Two more quick questions, Nadine.
If you look in the Weak Rocks book, chapter 4 in the Weak Rocks book, that's a good explanation of all that.
Yep. Two last quick questions, Nadine. Don't cut us off just yet. We've got a quick one from Daryl West. He's asking if you can provide any guidance on the angle of horizontal drill holes in terms of inclined or declined. He's tried a few different options and different materials, but asks for a bit more detail.
Again, site specific. So as a very generic rule, slightly down, like 4, 5, 6, 7 degrees down is better, for two reasons. One, they're more efficient if you drill them downwards because the driving head is higher if you drill downwards, because the reference point is the collar, not the end of the drain, so the driving head is better. The other reason is the holes stay full of water and don't fill up with air, and so the potential for chemical degradation, ion clogging, and other types of deterioration is less if you drill them down. The downside of drilling them down, or a reason to drill them up, is if you drill them down and you've got blast damage in the overbreak zone, let's say in the first 10 meters of the hole, if you drill them down, then you have more potential, because the water in the downhole is always pressurized. If you drill them down, you've got more potential for the water to come out of the drain, shallow in the slope, and enter the overbreak zone. Whereas if you drill them up, the hole is typically under zero pressure, so the water wants to run into the collar rather than into the overbreak zone. So two good reasons to drill them down, one good reason to drill them up. Depends on the situation, depends on what you're trying to do.
I see a question I just missed. earlier on from Nerlan Zumadilov. He asks if you have suggested methods for dewatering open pits in a permafrost region.
Yep. So typically you don't have to bother with the permafrost. So it's a good example would be Ikati diamonds in Canada, although there's Red Dog, we did similar in Alaska. So typically the permafrost stays frozen, and depending on the angle of the wall, depending on the orientation of the wall relative to the sun, a north-facing wall in the southern hemisphere actually cools down with time. So typically you can mine through the permafrost without very much problem. So the issue is, say if you have permafrost that's 500 meters thick and you haven't dewatered, you come out of the permafrost and you're into some quite large hedge potentially. So what the method for that is just some simple pressure relief holes into the floor of the pit to avoid the potential for high upward pressures and to avoid the potential for flow heave. And the vast majority of sub-permafrost groundwater systems are highly localized, so typically you can do your pressure relief holes in the base of permafrost with fairly low flow or fairly low sustained flow. So yeah, so permafrost you don't have to worry about typically, and sub-permafrost pressure relief holes before the pit gets out of the base of the permafrost.
Thanks, Geoff. And last question, David Rios asks if a water infiltration or falling head test in a pilot hole is enough to get a K value if you don't have any money to run a packet test or another test.
So the best thing to do in a pilot hole, I'm not sure. So a permeability value in a pilot hole can often be misleading. So if the purpose of that pilot hole is to look at a site for a subsequent production well, your best bang for your buck is to do an injection test. So you would drop a pressure transducer down the hole, depending on how deep the hole is, and you would use a water truck or some other means of injecting water, say for a 10-minute period, and then you would measure the rising water level as you inject it. So that gives you empirical data rather than theoretical data, and is typically a more robust method. So yeah, in injection tests and with reverse circulation drilling, you can put a sub on the top of the reverse circulation pipe, so you can inject water down the annulus between the inner tube and the outside of the drill pipe, and measure the rising water level in the inner tube of the drill pipe, and that is also very well documented in lots of different papers. So if you're going to do one test, injection test is probably the way to go.
And we use those to good effect in Zambia in RC drilling for a number of characterization projects. That seems to be all the questions. I hope I haven't missed anybody, but if you do have any questions, please feel free to email myself or Geoff. Our email addresses are on the screen. And there's also a lot of information on our website at www.piteau.com. That's PITEAU.com, as well as a list of publications. I will see if it's possible to get the links distributed to everybody, but if you're interested in the guidelines for open pit slope design and the guidelines for evaluating water in open pit slope design, the links are on the LinkedIn notification for this talk, and you can also find them, as I mentioned, on Amazon and on the CSIRO website. Well, thanks very much, everyone, and thanks to Nolene for setting everything up and for making sure that we've had an effective talk, and Sifiso as well, President of the GSSA, and to Matthijs Dippenaar, President of the Groundwater Division. Thanks very much for this opportunity.
I'd like to say thanks very much to Geoff for a fascinating talk. Gus, thank you so much for doing those questions. And to the delegates, thank you so much for joining us. We will see you next week, same place, same time. I'm going to end the meeting round about now. Thanks, everybody. Bye.
Thanks, Noeline.
Thank you.
Bye.
Thanks.